Sydney. Okay, now I get a little bit of feedback there, so it might be useful if you just mute your end, or otherwise I'll go a bit crazy. That's good. Okay. So thank you very much for the opportunity to speak, and I apologise for not being there. I'm a little bit jealous. I'm seeing lots of people who've come over for the meeting, but I'm pinned to Brisbane for the moment, so I thought this was the second best we could do. And it also wasn't clear that I'd have any video of you back at all. It turns out I do have a bit of video, so let's see, we have about 3 pixels each. So I can recognise John in the front row there. And I think I can see Chris Clarkson, not too far back. Good, okay, so I will get gross movement. So if you just grimace, then I won't see that, but if you fall asleep, I might. Okay, let's pick up my presentation. Where is it? Too many windows. Here we go. Okay, you got that all right? So the last time I gave this talk was actually an after-dinner talk. And I can see this now than an after-lunch talk, but an after-dinner talk is a much more difficult thing to do, because to talk about something as technical as debugging when people are expecting something just a little bit more relaxing is difficult. So let's see how we go after lunch. I'll try and stay on time. So yeah, I wasn't sure whether I'd have any pixels of you at all. So this is what I thought it might look like at your end. This is to trick me into thinking that there's an attentive audience at the other end. On the other hand, I may not be able to pick up sufficient detail to know whether, in fact, it's gone like that. And I guess without any audio back at all, I don't know whether that got any reaction at all. So. Okay, I get unlimited minutes. We can speak forever then. That's good. I don't know what happened there. Okay. All right, so what do... I don't know, can we get any audio back without my voice coming pouring back? Yeah, well, we'll try with that, see how we go. So I wonder if anyone wants to volunteer what the state of art in debugging is. This is a quote attributed to Edgar Dijkstra. I don't know whether it's accurate or not. No, we're going to have to shut down the audio. I can't talk with my voice coming back from Perth. So just mute it and we'll just go blind. This is a quote attributed supposedly to Edgar Dijkstra. You never know with these quotes whether they're actually real or not. But if I had a slightly more interactive audience, I'd ask what you really thought the state of the art in debugging was. And I'm pretty sure that you'd tell me it's something like that, language neutral. So most people, of course, finish up on supercomputers printing out the structures that they have. And I apologise to John that we've still got floating point numbers in there, but I'm sure that they could be non-floats as well. And then what's the state of the art in actually comparing whether you've changed a program and whether it does something different next time you run it is more often than not is printing out stuff and then doing a diff on it. That's sadly the state of the art. So we've been working for a good number of years on software tools around software debugging and parallel machines to make that a slightly higher level operation. So let me just spend a little bit talking about what it means to debug large codes, and I suspect some of the people in the audience have sufficient experience on doing this. There are a couple of challenges. One of them is what I call a cognitive challenge, and that is that we have a large number of processes, and so printing out structures from all of those processes is clearly not a very effective way of working out what's going on inside the machine. At the very least, that gives you problems with the user interface and how that scales. But the other problem is that these data structures are very large, and it's infeasible to examine individual cells of large floating point multi-dimensional array structures. The other thing is that heterogeneity is a great source of errors. And so when I work on machines that become increasingly heterogeneous, then that's often where the errors come from, that I might port a program from one machine to another or make small changes, and it fails when it's in this new environment because of something to do with something very slightly different, perhaps in the runtime of that. So that's how I think about what the errors might be. But the other one is a performance challenge, and that is that if I do any sort of high-level debugging, that turns out to be an expensive operation because the machines and the programs are, in fact, very large. And here's the observation I'll make, and then we'll come back to this at the end, and that is that the machines I'm using typically don't use the debugging techniques that I could use don't make use of that machine whilst it's sitting there doing nothing. So if you think about debugging a large program on a large machine and you stop at a breakpoint, you might be looking at what's going on inside the program, but the machine's sitting there not doing anything. And if you're trying to do something that is more powerful, wouldn't it be nice if you could actually use the fact that that's a parallel computer sitting there? As we move towards exascale, this is not going to get better, it's just going to get worse. So many years back, I and a number of my colleagues came up with this idea of what we called relative debugging at the time. It's been called comparative debugging for the last few years. And that is to try and track problems that arise when you port a program or change a program or something changes in an environment as I move from one environment to the next. So we call these evolved applications. They're large codes that are often constantly changing. That could be because the user changed their requirements. It could be because we've changed some of the algorithms, or it could be because we've changed the machine itself. And the kinds of errors that occur are often very subtle. Programs spend a lot of time trying to find those errors, to find this source of discrepancy and follow it back to the original source. And so as the machines get larger and the programs get larger, this just gets more and more difficult. So the idea of comparative debugging is actually quite simple in concept. The devil's in the detail about how you do it, but it's a data-centric approach. The idea is that we want to look at the data that's in one instance of a program, often called the reference code, versus the data that's in another version of the code that might be a development version. And at various points during the execution, we want to compare those structures. So the key idea, of course, is that the data should match in a new version of the code from what's happened previously. And then when you can do that, you can actually isolate variables that are deviating very quickly and find errors relatively quickly. Now, of course, this is what people do by hand when they're putting print statements in. They're invariably saying, here's the structure here, here it is over there, and tell me where they're different. I think you probably understand that that doesn't scale terribly well as the machines and the programs and the structures get much larger. So how does that help me with algorithm rewrites? It helps me with language ports, it helps me with different libraries and compilers, and it helps me with new architectures. And we've really done case studies across all of those different environments with slight variations along the way. So again, the key idea is relatively simple, and that is that we want to compare execution between two runs. And so we'd like to be able to assert things on data structures. And so for those of you who are familiar with software engineering concepts, the idea of asserting something within a program is not that unique. What we can do, though, however, is we can assert things between programs. And so I have a statement at the bottom that you don't have to parse the exact statement, but it says something along the lines of, I assert that this data structure big in this code at this line is equal to data structure small in this other code at data at line 300. And what the debugger does is runs those two programs concurrently, pulls the data structures back at those lines. So you might imagine it's actually planting breakpoints there. It's pulling the structures back somewhere and doing those comparisons and then returning control to the user. So what the user gets is something that says, I run your two codes and at this point these structures are the same or these structures are different. And so what you do in practice is you apply iterative refinement of the problem area. So here I've got my black code and I've got my white code, and I'm showing that at the end of the execution of one of these codes, the answer differs. And we actually sometimes don't talk about which one's right and which one's wrong. We have interesting case studies where the new code was actually the right one and the original code was the wrong one. However, the point being that the debugger detects the fact that the two codes have diverged. So they may be okay at the top and they may not be okay at the end. And so it's just a process then of iterative refinement in which I narrow down the code regions over which I'm looking. I say it's okay coming into this section, it's not okay leaving this section. And then so using an iterative refinement, very quickly I can narrow it down to a piece of code that is not that large. And so millions of lines of code can come down reasonably quickly through iterative refinement to a region where I'm actually prepared to look and then start to poke around inside the code. For those of you in the audience who are actually old enough to remember, we used to fix things like TV sets. And so this idea is the analogue of what I've seen in many repair shops, whereas someone may have a working TV set and a not working TV set, and literally with an oscilloscope or a voltage meter or something, looking between the two at the equivalent test points and saying, well, this is the signal I see here, this is the signal I see there, are they the same? And so it's really modelled on this idea that's been driving the repair of electronics for many years. Of course, these days we throw away electronics when it doesn't work. I'm not sure we're quite ready to throw away software just because it doesn't work. Now, one of the things we've done a lot of work with over the years is the role of visualization in this. And so if you're just comparing scalars and small numbers of scalars, it's not unreasonable to maybe show I've started these programs and that these things are different here and here are the values. So that very quickly scales out as I make my data structures bigger. And so here on the screen you can see a few different visualizations that we've worked with for showing errors. So for example, here is a 2D pixel map of some two-dimensional arrays where you can colour the differences between these arrays. Here is a much more complex visualization. I'll come back to this one in just a moment, these two, where these are isocircuits drawn around an error region, possibly in this case a time varying one. I'll come to this one in just a moment. And here's some work we've done with drawing statistical techniques for actually looking at the distributions of values that are in structures, and again trying to work out visually, in fact, whether programs are diverging or not. So it may be as simple as saying these two things are different, but scientific visualization plays a huge role for us in actually trying to decide how different they are. So this is some work that we did many years ago, actually. What you're looking at is a three-dimensional visualization of the difference between the temperature variables in two climate models. Now, the climate models were actually the same code, but some changes have been applied. And here you can see the error surface actually growing. So this actually gives you a lot of information about what's happening in the spatial domain of the error. It's not that it's wrong all over the place, it's that the codes are diverging, and in fact, as you're time stepping through these, the divergence is actually growing. Now, I actually took this picture and took it to a colleague of mine who's a climate scientist, but didn't know the details of the experiments, and said, what do you think about this? And very quickly he said, well, actually, I think there's not one error, I think there's two. And he did that by looking at the visualization and seeing that, in fact, some of these errors were occurring around the lower regions of the atmosphere and some were occurring around the upper regions. And the time movie showed that, in fact, they were growing independently. And he also happened to know that the physics at the bottom of the atmospheric models was different. So he had hypothesized pretty quickly that there were two errors. And in fact, you can't get from the bottom of the atmosphere to the top of the atmosphere in one time step anyway. So turns out he was right. To cut a long story short, there were two errors. One's in the long wave radiation code at the top here, which is where the sunlight enters the atmosphere, and there's physics to do with what happens when sunlight interacts with the atmosphere, versus the planetary boundary layer physics, which is a completely different piece of code. And one turned out to be the error in the radiation time step code, and the other one turned out to be more complete physics, not actually wrong, but more complete physics in the new version of the model in the long wave radiation code. So this was kind of really quite remarkable that you could show these visualizations to someone who didn't have the code in front of them, and they were actually able to isolate pretty damn well which regions of the code were misbehaving or behaving differently, I should say. We've done other work here. Here is a visualization, in fact, of two versions of a code. It's a particle code modeling, smooth particle hydrodynamics code modeling what happens when you drop a brick into a two-dimensional tank of water. On the left-hand side are two different runs of that code with the brick in the same position. And it's a bit like the Where's-Wally experiment. You could try and work out that actually, yes, I can see some blue particles up here that are not there. And when the more you look at it, the more you see that's different. It's like those little things you do in the magazines. On the other hand, here is a visualization of the difference. And I'll just play that again for you. And you can see in this region here, this is where it starts to diverge. The size and the color of these glyphs is actually showing you how much the codes are diverging. Here's another error. Now, it turns out that those regions are around the boundaries between processors where inter-process communication is occurring. So by looking at the fact that the error starts in one place and propagates out, you might hypothesize that the error in this case was to do with inter-process communication. Data values not being correctly transferred between one process and another. And again, that actually turned out to be the case in point. Let's have a look at how we're going for time, talking about scalability. We'll see if we can scale this down. So one of the problems is that the original idea of how to do this was way too simple. And this is a complicated picture, but what it does is shows you the infrastructure we put in place in our earlier versions of this debugger to instrument the code. And so actually what happens is there's debug servers attached to each of the processes, and what these do is get the bits of their data. Remember, the data is usually decomposed across large structures. This is copied back to a head node, combined to reform the reference data structure, combined to reform the suspect data structure, and then compared. So we talk about copying, combining, and comparing. Anyone who knows anything about parallel computing will tell you that that doesn't scale, and in fact we never managed to make this work on more than very, very small machines. So clearly that wasn't going to scale to the class of machines we're interested in today. Here's a more complex picture. Again, I won't drill into it given the time, but we come up with a couple of techniques that allow us to use the underlying parallel machine. So remember I said that the tragedy is my machine's sitting there doing nothing, and it could be doing something to help the debugging. Well, we worked out how to do that. And in fact, these debug servers now extract the data from the programs as before in parallel. And then we had some fairly sophisticated hashing algorithms that actually hash up the substructures and send signatures back to the head node. And so, in fact, you don't get the reference data structure back in the head node, you get a reference signature array, which is orders of magnitude smaller than the data structures out in the servers. And these are actually compared. And there's a whole talk I could give on telling you how you can make that work. So at the moment, you'll just have to trust me unless we get a chance to talk more about it. There's another way of doing this, and this is to say, well, you've got a parallel machine there. Why don't you use the inter-process communication of that machine to do the comparisons? And so here what you do is you extract the substructures, and then you do a parallel compare by sending part of one structure and part of another structure to corresponding processors and get them to do the work. Now, there's a lot of detail in that about how you make it work, what happens when you scale the application so that the amount of data that's there changes. So, and I don't really have time to talk about that, but you'll have to trust me. Now, remember I said the heterogeneity is a great source of errors, and it turns out that you then also have to make your debugger handle heterogeneity. So the thing is that data structures aren't represented in the same way in all of the processes that you might be looking at. You might go from a GPU to a CPU where the floating point size may change or exact details may change. So we map our data structures into an architecture-independent format, and we do the comparisons on that. And so the debugger has a native architecture-independent representation where it does its comparisons. There's a lot of flexibility. Usually I get a question at this point about, well, what do you mean by equals? Well, equals actually doesn't mean exactly equal. It means equal within some tolerance. We have the ability to talk about data structures being not being strictly type conformant. So I may, for example, reorder structures, but as long as I've got the same number of elements, I can do comparisons between them. You can take subarrays, you can do cross-language work and the like, and we've even done some work with dynamic data structures. So there's a lot of complexity in what it needs to talk about doing comparisons as well. Some of our more recent work has been comparing cross-programming languages, and so we can take things like a C program and compare it with a program written in OpenACC or OpenMP. Again, there's a lot of heterogeneity that comes in having different programming languages. We've done some work with UPC, in which you have a global global memory space, and again, comparing that between different runs of the same code, or variants of the same code. Most recently, we've been working out what does it mean if you don't have a reference code, and this builds on the idea of being able to make assertions about what a data structure should look like, rather than saying it should look like what's in that code over there. I might say, can I say something about the statistical properties, for example, of this? Now, it turns out that if you have a good enough understanding on the mathematics in some of the models, you may be able to say things like, well, this thing should be normally distributed, or there should be an average around this value, or the standard deviation should be within certain bounds. And so we've done some work most recently with building what we call statistical assertions, in where you say things like the ones I just gave you, that this thing should be within some sort of bounds. And that means that I can then run my code and verify it against some a priori model to look for errors, not to say that it's right, but to say that it should be within certain bounds. And then you can get things like visualizations of that, and here you can see some histograms in which here I might say that this is actually a particle model, and I may be able to say something about the distributions of speeds in this model, and this is what it might look like in an incorrect code, but in the reference code it should look like this. And so I can say things like compare these two histograms. And so we've done some work on that most recently. Okay, so what's the status? Well, it turns out that if you buy a Cray, not being a Cray salesman, I'm not advertising them, but you actually get our debugger for free. So if you pay multiple $1 million for the machine, you get a free debugger. So that's kind of nice. This is available on all the Cray machines. So it's called CCDB, the Cray Comparative Debugger. As I said before, this is pluggable across quite a few different programming environments. It's built on a scalable library called MRNet, which scales out quite nicely across the machine, and we have run it on some quite large configurations of machines. So let me just close with saying, well, what does it mean to go to the exascale? What do we know about exascale machines? Well, they're probably going to be big, they're probably going to be heterogeneous, they're probably going to have mixed precision, they're probably going to have hierarchical memories, and the algorithms are going to change. So have we made any progress towards those things? To do that, we think you need, well, in fact, these are some of the items identified in this report. You need scalable debug techniques, you need debugging across hybrid and heterogeneous architectures, you need specialized memory systems, you need domain-specific languages, you need mixed precision arithmetic, you need adaptive systems and correctness tools. And I'm not going to pretend that our relative debugger addresses all of those, but we think we've made a bit of progress on some of these topics. So I won't dwell on that. Can I just finish by advertising a couple of conferences that are on in October? So the eResearch conference is in Brisbane in mid-October, and the eScience conference is in Auckland the week after that. So anyone who's looking for an excuse to go touring around the Pacific, you're very welcome to those two events. Well, now, what I don't know is, of course, whether there'll be raucous applause, but I got myself an image of that as well. So I'm going to finish on that note, and I think we might have 2 minutes for questions if you want to pass the microphone around.
I was very tantalized by the two-layer error in the weather model that you had, the lower atmosphere and the upper atmosphere. But I kept waiting for you to say what the discrepancy was caused by exactly. And you said, yeah, we got two different differences. What caused the difference? Because you submitted the same code to two different machines. What was that's a bug. Something's not working. That's a bug.
Right.
What was the bug?
So in that particular example, there were two bugs, one in each code, and one of them was to do with the change actually in the physics. So it wasn't actually a bug, it was just that they put more complete physics in. But John, you'd appreciate that the interesting thing was there that no one could actually tell us, and the hypothesis, the floating hypothesis was, oh, that's just floating point divergence. So I'm sure you'd be very glad to hear that. In fact, we've had many cases where people have just put it down to floating point differences.
Wow.
And in fact, in some cases, we've found quite distinct errors.
Well, I'm not glad to hear people so tolerant of it, but yeah, I know what you mean.
Well, one of the codes was actually a bomb code, so you shouldn't worry about that these are used in important places.
This seems like it's very much geared to really large existing code bases where no one wrote unit tests or anything like that to begin with. Is there sort of a workflow for taking this comparison between two different versions of a code base and then extracting what do you think it should look like, and then turning that into something more along the lines of an integration or unit test that you can then have as part of the development workflow for people who go and tweak the code further?
Yeah, that's a great question. Thanks for that. There's actually a lot in common, of course, between standard testing techniques and this. And sometimes we call this a test environment, and sometimes we call it a debugger. So the bit where it becomes a debugger is it's highly interactive. Now, we have done work in the past where you could put these assertions actually got built. So at the moment you build them manually, you say, I assert that this should equal that. We have done work where we put partial assertions in the code, and you just say, look, data structure phi is a good one to watch. And then you can build scripts that go through versions of that code and pull them out, build the assertions and do the runs. You can also then actually capture the output of those runs and maybe use those in testing. So you're right that there's a strong relationship between test and debug here.
Great, thanks.